Hello and welcome to the Poor Richard Sailing Research channel, I suppose. I tend to be a little more science oriented than most. So this time, my friend Russ Whitford of the sailing vessel Tumultuous Uproar asked me if I could model the Coriolis effect and whether or not it actually creates the need for more twist on starboard than on port tack. I found this very interesting. I had done a model of how the Earth's boundary layer, because of the friction of the Earth, um, creates more wind at the top of the sail than at the bottom, really. And that's the dominant reason why we need twist. So I set about trying to figure out the Ekman spiral, really, which is what happens from geostrophic winds aloft in the planetary boundary layer, which is very, very thick. Can be a couple hundred feet, a couple thousand feet. It all depends on the Rossby number and the Zilichek number or something. I forget. That might not be pronounced correctly, but there are some really good papers on the subject, and I found them and allowed me to create um, a quantified model of the Ekman spiral in my simulation. So, without any further ado, let's go ahead and get into that. Okay, here we go. So, what we have here is a model of the points of sail, but it's a whole lot more elaborate than that. Okay, so we're starting out where there is no boat speed, and without any boat speed, the apparent wind is the same as the true wind. And this is the basic epiphany of sailing, as I call it. Okay, and that is that the sail is at the same angle to the apparent wind, or the wind that you apparently see from sitting on the boat because you're moving along with the boat. Okay, in this case, we are stopped. The apparent wind is the same as the true wind. Okay, so we can change our heading. The sail has to be adjusted to match at the correct angle to make us go forward. And the force that's pushing us forward is coming from the sail along approximately this vector here. Okay. Um, if we tack over, we have to switch sides on the sail and do the same thing. Okay. So it's the same. This is on port tack and this is on starboard tack. Okay. We can't sail in the no sail zone because it just won't work. The physics don't work out there. You end up just luffing your sail. Okay. But we don't really live in a world like that. We do when we're on the boat, I suppose. But in the real world, we're actually moving along, and there's a vector for boat speed here, okay, represented by the blue vector, the arrow, right, that I'm changing the length of, okay. And then we have the true wind, which is the brown vector. It's lined up with the wind in this head to wind direction, which is straight up and down in this. The only reason we do that is so that if we tell you to head up, that means toward the wind, or if we say head down or bear away, go away from the wind. Okay. So now that we know that, we also can find out that this is not really just a simple situation where you have boat speed and one apparent wind vector and one true wind vector and all this stuff. Is really happening in 3D. So if we go to 3D and we move these views around, because I had them kind of a little bit weird here, we see that we're really kind of in a 3D world. Okay. Well, in this 3D world, we actually have a little bit more complexity by the wind power law, which is approximately like this. We'll see how that turns out. This is dragging on the ground, okay? The wind is dragging on the ground and causing shear throughout the layers in the very lowest layers called the surface layer of the planetary boundary layer, which is considerably small compared to the boundary layer. It's like 0.01 to 0.03 or something, the height of the boundary layer, okay? If you're considering mast height of 50 feet. This sail is, once again, arranged with the same size as on my Hunter, okay? So then what you can see is, as you resolve the boat speed vector, right, which is the blue one here, which is the same all the way up and down because it's the mast is mounted on the boat, right? Unless you're in waves. When you go into waves, then the mast will be rocking forward and back and causing some differences as it does that. But generally on flat water, it's going to be the same all the way up and down the mast because the mast is mounted on the boat, okay? So if that true wind changes, right, it's changing this way. That's causing a change in the triangle of the wind velocity vectors, okay? The boat speed and the true wind combine to create the apparent wind angle. As you can see over here, there's a large variation from near the ground to the top because of this logarithmic increase in wind as you go aloft, okay? Or decrease in wind as you come down. Well, in the Ekman layer, from the geostrophic winds coming down, that actually trails off to the left. Aloft, it tends to go along the isobars if you're looking at the pressures of a low or a high. But down near the ground, from our point of view, on the other end of the Ekman spiral, it tends to twist off to the right as you go up, okay? And the maximum is about 3 degrees. This is showing 3 degrees, right? I can exaggerate that by adding more divisions, but we're just going to stay with 10 for now, okay? So that does indeed cause the need for more. Well, let's change our sheeting angle here so we're not oversheeting. Put it back in the middle. There's this is simple vectors, right? There is some upwash that happens at the front of the sail, and that's really interesting. Okay, and then we can look at this in the perspective view, right, and see whether or not we have. Well, what I've done here in my model, by the way, is tell these curves, okay, the sail curves, to remain at the same angle I set them at when I first set up the angle of incidence, okay? So let's go back to the top view. So just like when I first started this thing, if I change my heading, that sail stays in lockstep. But as I bear away, the required twist is greater than if I'm beating to windward, just because of the twist, the deficit in the sail and the potential for the Ekman spiral to influence the surface layer. This won't always happen. It varies as the sign of latitude. So at the equator, you won't see this. You will not see Ekman spiral at the equator. It just won't be there. At the poles, it'll be a maximum. And somewhere in between, probably a fraction of that. But I would guess I think it's 60% from what I calculated at my latitude, which is on the Chesapeake Bay. So Ekman spiral does, in fact, cause the need for slightly more twist in the sail on starboard tack versus port, okay? Which is really very interesting indeed. And the reason for that is because Ekman spiral is always going to be going slightly to the right aloft, right? So let's do it from here, okay? I'm going to change the Ekman spiral in my model. More and less, okay? More and less. Well, we're on port tack. So you can see as it does more, it's actually flattening or untwisting the top of your sail. So let's go back onto starboard. Okay, now we're on starboard tack, and we're going to change the Ekman spiral. Right, here's less, and here's more. Indeed, it's causing the need for more twist on starboard if, in fact, you are seeing the Ekman effect. There are a lot of other dominant processes in the atmosphere that mean it's not necessarily going to happen, but it can on large bodies of water, like big lakes or a big bay like Chesapeake, or in the ocean. And it also says that if you have a puff, you're more likely to get a lift on starboard tack than you will on port. However, a puff, if you look at true wind speed, as you get more wind speed, it tends to give you a lift anyway, right? So, but persistent lift will probably be more likely to occur on starboard tack than on port tack, especially in the ocean, okay? Which I find really very interesting. So let's go back and we'll talk about the Ekman layer a little more. So here is a diagram of the Ekman spiral as related to the planetary boundary layer. And as you can see, their coordinate system begins at the source of the wind, and they are looking downwind, okay? Whereas in sailing, we're actually heading upwind a large number of cases going upwind, right? So we're looking upwind usually. So that's why they talk about it veering off to the left, but we see it veering off to the right. We hope you enjoyed this edition of Sailing Poor Richard. It's a little bit off of the adventure and actual sailing that we would really love to do, but it is in the middle of February, so we'll get back to it. Spring break's coming, so we'll be out sailing very soon. Have a great day.